In this recording, we will have an introduction to inverse functions and a simple example. And for a function y equals f of x, for each value of x, there must be a unique value of y if it is in fact a function. Furthermore, when a function y equals f of x is strictly increasing or strictly decreasing on its whole domain, then for each y value in the range, there will be a unique x value in such a case. And a function of this type is called one-to-one. And so for an example visually of such a case, you might have something like this picture here, which is an example of a strictly increasing function, because as x increases, y always increases. And if we have a one-to-one function f of x, then the reverse relation will also define a function called the inverse function. And this will often be written with this notation f and then a -1 superscript for inverse, f inverse of x. And if y equals f of x, it follows that x will equal the inverse function applied to y. So let's have a look at how we can find an inverse function and then look at an interesting visual property of functions and their inverses. So let's look at an example. If we have a function f of x equals 2x plus 3 divided by 5, let's find the inverse function, f inverse x. And for convenience to do this, because f of x relates to the y values, when we put different values of x into this expression, for convenience, let's call that y equals 2x plus 3 divided by 5. And one method of finding the inverse function can then be to interchange x and y. That is, everywhere we see y in this expression, which is on the left, we write x. Everywhere we see x, we write y, giving 2y plus 3 divided by 5, on the right in this case. And then we rearrange that for y, which will then be y corresponding to the inverse function. So if we're going to make y the subject of this, we would start by multiplying both sides by 5 to get 5x equals 2y plus 3. We could then just swap the equation sides around so that y is on the left hand side. So 2y plus 3 equals 5x. Trying to isolate y, we could then subtract 3 from both sides, giving 2y equals 5x minus 3. And finally, we could make y the subject by dividing both sides by 2, so that y equals 5x minus 3 divided by 2. That is, in this case, the inverse function of x is in fact 5x minus 3 divided by 2. And you might recall we said if y is f of x, then x is the inverse function of y. So let's just put in a value of x just to demonstrate this. And if you look at the original function we started with, y equals 5x minus 3 divided by 2, that is a straight line with a positive gradient, so that function is always strictly increasing, and any value of x will give a valid value of y for this linear function. So any value of x we could put in here to demonstrate the property. So let's, for example, just put in, let's say, x equals 3. Then since our original function was in fact f of x equals 2x plus 3 divided by 5, f of 3 is going to be 2 times 3 plus 3 divided by 5. That works out to be 6 plus 3 on 5, which is going to be 9/5, or 1.8. So if we put that value into f inverse x, which is 5x minus 3 divided by 2, f inverse of 1.8 should be equal to 3, going back the other way. So let's see if this is in fact the case. F inverse of 9/5 is going to be equal to 5 times 9/5 minus 3 divided by 2, What does that work out to be? That's going to be 5 times 9/5. That will just be 9 minus 3 divided by 2, which is going to be 6 divided by 2. Sure enough, that's equal to 3. So we saw that f of 3 was equal to 9/5, and then going back the other way, applying the inverse function to 9/5, we got back to 3. And that same property would happen for any value of x we used in that way. Now, a final thing to note is there's an interesting visual property of inverse functions. Now, and this can be seen if we plot f of x and the inverse function of x on axes where both of the axes, x and y axes, have the same range. So in this case, using Wolfram alpha, the x-axis and y-axis both extend from -5 to 5. And the original function f of x is actually this line here. So that's our 2x plus 3 divided by 5, while the inverse function is the line that's shown in purple here. So what is interesting is that if we were to also add the line y equals x onto this graph, which here is shown in orange, you'll notice because we have plotted the axes on the same scale, f inverse x is a reflection of f of x about the line y equals x. So that is also an interesting visual property of a function and its inverse. So in subsequent recordings we will look at a more complicated example where the initial function is not one-to-one and where therefore we need to restrict its domain. So you might also be interested to look in that example.